This is a Silvero Minak. So today we will just study fluid mechanics, and this is mainly from the exam oriented point of view and the revision point of view, so that like if you are going to do for an exam like state A's, J's, or any exam like for a brief revision, we'll just revise the important things so that we can do some major numericals in the things, and also attempt the MCQs in these exams. So that will be the approach. A very detailed study if you want to do, obviously you need to study the textbooks, but here if you just do this, then you will have the idea, and to if you are in regular BTech course, you will be able to attempt major numericals, and also if you are attempting the competitive exams, these are the main portions from which the numericals are solved. So that's why I'm just focusing on these things, and from the exam oriented point of view. So let's start. So fluid mechanics, when you need to solve a numerical, the first thing which you need to know is the viscosity part. Okay, so we need to know and understand what is viscosity. By the way, I am just doing this lecture, not I have not written everything and then telling you, so doing this lecture in real time. So you can also just take your, if you want to just study, you can also take your pen and paper and then start just the lecture, and also keep a calculator with you, because we'll be solving numericals as well. And like this, in all my series of this civil engineering subjects, every subject as strength of materials, surveying, and all the other subjects which I have covered or I will cover, these have the same approach. The majority of the numericals you are able to solve, and also the important theory parts, that only I'll tell. I'll not teach the entire thing. So minimum knowledge for interviews, for competitive exams, you will get through it. So this is the bare minimum. And the so you should just revise, uh, take out some time. If you are doing job 1 hour, 1 hour or 2 hour, take out some time and revise these things. It may come in handy if you want to just appear for an exam. Okay, or be it an interview or a regular exam. Okay, so first of all, we'll look at what is viscosity here, right? So viscosity is basically, you can just write here, viscosity is basically the property of a fluid uh, which offer resistance, to the, it will offers, right, offers resistance to the movement of one layer of fluid over the another adjacent layer of fluid. Okay, offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. So we have this simply a fluid here. Let's say if you fluid here, it is flowing in this direction. So the resistance which is created in between the two layers, property of fluid which offers resistance to the movement of one layer of fluid over the adjacent layer of fluid, this is known as the viscosity. So it is concept is pretty much simple, but the definition we should also know here. So now comes the major things which we need to know. So first of all, you can draw this diagram here, which you'll find in every suitable textbook. Here this is the diagram and the velocity near a solid boundary. So this is a solid boundary, let's say. So you can say this is the figure, velocity near a solid boundary. So this is a velocity of the fluid near a solid boundary, and it is flowing at a, let's say, at a speed of u. Okay, this flowing at a speed of u, and here this is the, you can call it the velocity profile, right, profile, and it is flowing at a speed of u, and this is u plus du, because the velocity is more here. Okay, and this thickness, this one, it is dy. Okay, delta y dy. So this is it. Now we'll explain what is this actually. So the relation which we have to remember is tau proportional du dy. So this is we have to remember. Now everything we'll need to know what is tau. So tau is the shearing stress. Tau is the shearing stress, and mu is the constant of proportionality. So mu is the constant of proportionality, and if you just equate this equation, it will be tau equals to mu into du by dy. So now this mu is the constant of proportionality, tau is the shearing stress, and this mu is also called the, this constant of proportionality is called the coefficient of dynamic viscosity. Okay, we know about viscosity. Now this is the coefficient of dynamic viscosity, mu. This is more commonly just a called name. And what is the du dy? So du by dy, here it is the shear strain rate divided by the shear deformation. So shear strain rate divided by shear deformation is the del u and by del y. So this equation you need to remember. Now this law is called, this law which you just have remembered, this is known as your Newton's law of viscosity for fluids. So it is called Newton's law of viscosity for fluids, and the fluids which follow this rule are called Newtonian fluids. Major fluids like water, air, molten metals, these are Newtonian fluids. So Newtonian fluids, example, it can be water, air, molten metals. So majority of these are the Newtonian fluids which obey this rule, that is Newton's law of viscosity for fluids. Okay, so this is the rule, and you will find many numericals for that, and sometimes this will be called shear strain rate, sometimes it will be shear deformation, and also it is also called sometimes velocity gradient. So they called by various names, but shear strain rate is the most common one. Okay, so now let us come to the next thing, that is the unit. So the major thing which you need to know is the unit of mu, or the dynamic viscosity, coefficient of dynamic viscosity. So here first of all let's see the SI unit. Okay, so SI unit will be Newton second per meter square, right? The SI unit will be Newton second per meter square, and in the CGS system, centimeter gram second, CGS system, it will be unit will be your dyne second per centimeter square, and dyne second per centimeter square is also can be written as poise. Okay, so the CGS unit is poise and the SI unit is Newton second per meter square. Okay, you will find these two units most commonly used, but whenever you will do numerical, always you will convert to Newton second per meter square. So if in a question the values are given in poise, we need to convert. So you need to remember this relation: 1 Newton second per meter square is equals to 10 poise. Just remember this relation: 1 Newton second per meter square is equals to 10 poise. Then you will be able to solve all numericals, right? So let's move forward and head over to this kinematic viscosity. So right now we only learned about viscosity. Now we will learn about kinematic viscosity and how to do the numericals. So the next section will be our kinematic viscosity. So for doing the numericals, for that you have to know kinematic viscosity is denoted by mu, and now mu is equals to viscosity by density. Now viscosity we already know is denoted by mu, and density always denoted by rho. Okay, so mu and divided by rho. So the unit, ultimate unit which comes is, if you just evaluate this, it will come as length square by time. So the, if you talk about the units, okay, first if we just see the SI unit, the SI unit length square by time will be obviously meter square per second, and the CGS unit, question in questions often there you will find CGS unit mentioned, it is centimeter square per second, or and centimeter per square second is called Stoke. Okay, so if in the question the unit is given in Stoke, so you have to convert it. So now how can you convert from Stoke to SI? Well, it is centimeter square per second, you have to convert into meter per square per second, right? So Stoke centimeter to meter, if you convert, it will be 1 by 100, that is 10 to the power minus 2. If you multiply, then it will be converted from centimeter to meter. Similarly, if for centimeter square to meter square, it will be 10 to the power 4 minus 4. So Stoke into 10 to the power minus 4 is equals to meter square per second, right? So centimeter per centimeter square per second is Stoke. You have to remember that, and Stoke into 10 to the power minus 4 is meter per second. You will just get the answer, and always while solving the numericals, make sure you solve in the SI units. Okay, so then you will have a common thing by which you can solve. Now get ready with the scientific calculators, because we will solve the numericals, right? So let us write the question first. So the question is, just write the question here along with me. A plate 0.025 mm distance from a fixed plate moves at 60 centimeter per second and requires a force of 2 Newton per meter square to maintain the speed, right? So determine the fluid viscosity between the plates. So we have a plate here, and the diameter is given. So first of all we'll write whatever we know here, right? So what do you know? So we know that the fixed plate moves at 60 centimeter per second. So U is 60 centimeter per second, and we know that always you need to convert in SI unit. So it will be 60 centimeter means 0.6 meter per second. So this is your U, right? So now we know U, and the next thing which is given, as you can see, this is 0.025. So means dy is given. Okay, so dy, if you just write here, dy is equals to 0.025 mm. Quickly convert it into meter. So it will be like, let us write 0.025 into 10 to the power minus 3, right, meter. everything converted into SI. And the next thing which requires it is a force, and as you know from the relation, that is Newton for the force, or the Newtonian's law of viscosity for fluids, tau equals to mu into du dy. Now tau is the shearing stress. So the shearing stress, as you can see from the unit also, it is written force, but it is actually here stress here, 2 Newton per meter square. So that we have to know here, tau equals to 2 Newton per meter square. So that is given in SI, so no need to change this. So we know tau, we know here dy, we know u. Now what will be du? So du is change with respect to this. So as you can see, moves at 60 centimeter per second. So earlier it was like 0, right? 0 to 60, right? So it will be 60 minus 0, right? 60 minus 0 du. So it will be 60 in turn 60 centimeter per second, or equals to 0.6 meter per second. So du we know. Now what is required is mu. So using the relation, tau is equals to mu into du by dy, right? So implies mu is equals to tau into dy by du. So tau we know 2 Newton per meter square, into dy we know dy is equals to 0.025 into 10 to the power minus 3, divided by your du we know 0.6 meter per second, and this unit is obviously your meter. And now if we just evaluate this and do it by our calculator, the answer will be your 8.33 into 10 to the power minus 5. The unit will be Newton is up, and meter, as you can see, meter, this will be cancelled by this. So and it will be Newton second, right? Newton second will go up per meter square. So this is the answer, and this is the value of mu. So this is a quick numerical, so that you can summarize it. You can also take a screenshot if you have, and if you have done it along with me, then it's very good. Or you can just pause a minute to just see what we have done here, and then you can move on to the next numerical. Okay, we'll do some numericals so that we can just understand and ease into the mood, right? Now once you know that using this formula how many numericals you can do, you will be shocked that most of the numericals you can do using this formula. Okay, so it's very good. So now the next question which you have is of kinematic viscosity, right? Means nu will come. So this is also very important, this type of questions. Find the kinematic viscosity of an oil having density 981 kg per meter cube. The shear stress at a point in oil is 0.2452 Newton per meter square, and velocity gradient at that point is 0.2 per second. So try to find the kinematic viscosity of an oil of 981 kg per of having density 981 kg per meter cube. The shear stress is given here 0.2482, and the velocity gradient is also given here. So what do you need to do? Okay, so answer. So first of all, just see what is written here. First of all, we have here our density. So density is 0, so it is 981 kg per meter cube, right? So kg per meter cube we won't change, it's not required to change if the unit is given in kg per meter cube. And then the shear stress of a point is written here. Shear stress is tau, So tau unit is also given in SI 0.2452 Newton per meter square. So no need to change it. And then the velocity gradient. So velocity gradient is the du by dy. You know that 0.2 per second. So du by dy is equals to 0.2 per second. So these three things are given here. So now we know what is your mu, right? So tau, using the Newton's law, tau is equals to of viscosity of fluid, tau equals to mu into du by dy. So we can easily find from here what is mu, right? Mu is equals to tau into 1 by du dy. So tau is your 0.2452 and du by dy, if we go in the divide part, it will be 0.2. So now mu comes as, mu is equals to this 0.2 unit is per second, right? And this unit is Newton per meter square, right? So 0.2452, I'm just doing in the calculator, 2452 divided by 0.2, so it will be 1.226 unit will be Newton, second will come above per meter square. So mu is 1.226 Newton second per meter square. And now the kinematic viscosity, right? So you can write here kinematic viscosity, because that is the thing which they asked in the question. Kinematic viscosity, mu. So what is mu? Mu is equals to mu, that is the normal viscosity, by rho, the density. So viscosity we know 1.226, we just found out, Newton second per meter square. And rho, if it is given in kg per meter cube, don't need to change anything, just put it here, 981 kg per meter cube, right? How it came, we'll just show it, but right now just do it now. 1.226 divided by 981, right? So the answer will be 1.249 into 10 to the power minus 3 meter square per second. So as you know, the SI unit will be meter square per second, and rho, if it is in kg per meter cube, don't need to change anything. And if it is not in kg per meter cube, bring to kg per meter cube, and then you can solve the question, right? And if you want to get the clarity about this unit, how this unit came, I am willing to show you, because the clear concept is always very important, though it is not important from the exam point of view, just for clearing your concept. So Newton second per meter square is the unit, Newton second per meter square, right? And this unit kg per meter cube is down, so meter cube by kg, right? So first of all, meter and meter will be cut, so meter will remain. So it is Newton second, okay? It is Newton second meter by your kg. So Newton second meter by kg. Now what is Newton? Newton is your meter square per second, okay? M into A, okay, right? So meter square per second. So now kg, so I know it is meter per second square. So F, that comes from the formula of F into mass into acceleration. So mass in kg, and acceleration unit is meter per second square, right? So the unit of Newton will be this kg meter per second square, right? So this is the thing, this is the concept behind this. So the unit of Newton is kg into meter divided by second square. That's I have written by Newton right now. And we already have second meter by kg. So first of all, kg will cut, second, this second will cut this second, 1 second will remain. So what is remaining? What is remaining here? Meter square per second. So that's how this unit came, meter square per second, right? So this is the explanation, and if you want to just go into details, this explanation is required. And just remember everything, if you take the density in kg per meter cube, then it is good, right? So this is it about this. So the next section, which will be in the form of numerical here. So we'll do next numerical. Now we have done two numericals of two different types. Now we'll do some more and go a little bit deeper. This one is easy one, and next one will be a little bit more the concept which is used. So write down the question. So this will be determine the viscosity of a liquid having kinematic viscosity, 6 Stokes and specific gravity 1.9. So this is it. So determine the viscosity of a liquid having kinematic viscosity 6 Stokes and specific gravity 1.9. So now kinematic viscosity is 6 Stokes, and I already told you the relation between Stokes and your SI unit. So Stokes is basically, you can write it as 6 centimeter square per second. Now 6 centimeter per square per second is equals to 6. We'll just write here 6 into 10 to the power minus 4 meter square per second. So this is the unit which is comes in meter square per second. Okay, so and this is what this is one important conversion, and if you remember the poise, then 1 Newton second per meter square is equals to 10 poise, so which is the unit of mu as well, right? So or poise by 10 is equals to Newton second per meter square. So that's that, in that way you can convert. If the unit is given in CGS, in often in fluid mechanics problems the unit is given in CGS, right? And what else is given? And the specific gravity is given 1.9. So specific gravity, if it is given 1.9, specific gravity is 1.9, then rho is equals to 1.9 into 10 to the power 3 kg per meter cube. So now how do you come to that conclusion? So we know specific gravity is equals to density by the this density of the liquid by the density of water. So the density of water is 1000 kg per meter cube, right? So what will be the rho? Rho will be specific gravity into your density of water. So like that you get the density of liquid. So whatever the specific gravity is given, just multiply into 10 to the power 3, you will get the density of the liquid. So that is very simple explanation for that, as simple as it can get. So viscosity in simple mu we need to get. So tau is equals to, that light the relation, so it will be, sorry, du by dy. So write the relation again and again so that you can remember. So du by dy, and now we don't know mu, so we have to find out mu here first. So to find out mu, we know we have nu and rho. So nu is equals to mu by rho. Now mu is question mark, so implies mu is equals to nu into rho. So it means just write down the values. 6 into 10 to the power minus 4, 6 into 10 to the power minus 4, and that will be meter square per second, and into rho. Now rho will be 1.9 into 10 to the power 3, 1.9 into 10 to the power 3 kg per meter cube. So now if you multiply this in calculator, 6 into 1.9, it will be 11.4. So 11.4 into 10 to the power minus 1, so it will be 1.14, and the unit we know for mu is Newton second per meter square. And also I will revise you the relation. 1 Newton second per meter square is equals to 10 poise, right, for the CGS unit, because you never know, you need to know the relation. Okay, so mu you know from here, so that's what is required for this. And in this question, this relation is not required. only this one is required, that is the relation for the between the dynamic viscosity and the normal viscosity of the liquid. So now we'll do another numerical in which the two formulas which you know will be used, and the formula for the rotating shaft will be used. Now the formula for the rotating, this shaft, this tangential velocity of the shaft, this is common, and torque and power. So these question you can find, like one question you can find in almost every this competitive exams. This is very common type of questions, and not only in fluid mechanics, it can come in other part as well, and the formulas are the same, right? In solid mechanics also it is there, in fluid mechanics also is there. So this formula for the rotating shaft is same, and you might expect a question in any competitive exam out of this. So let's write down the question first, right? Write it along with me. The dynamic viscosity of an oil used for lubrication between a shaft and sleeve is 6 poise. Now you already know the relation for between poise and your Newton second per meter square. What is the relation? 1 Newton second per meter square is equals to 10 poise, right? Okay, let back to the question. The shaft is of dia is equals to 0.4 meter and rotates. Now this formula you don't know if you at 190 rpm. This formula you don't know if you haven't solved this type of numericals earlier. If you have, then you obviously know. I'll give you the formula, then you can solve it. Calculate the power lost in the bearing for a sleeve length of 90 mm. The thickness of the oil film is 1.5 mm. So the dynamic viscosity of an oil lubrication safe is 6 poise. Whenever poise comes in mind, remember that poise is your, what is poise, right? So poise is the unit of your viscosity, right? So it is written dynamic viscosity, but it will be obviously viscosity. So now mu is equals to 6 poise. So 1 Newton second per meter square is equals to 10 poise. So it will be 0.6 Newton second per meter square, right? So now we know this is the dynamic viscosity, and nu is called the kinematic viscosity, right? So dynamic viscosity is 6 poise now, and nu is the kinematic viscosity, which will not be used here. Okay, then what is given? The shaft is of dia 0.4 meter. So just let's write d is equals to 0.4 meter. Oh, before writing all the things, I'll just write you the formula, because we don't know the formula, right? Okay, the formula for the tangential velocity of the shaft. Now the formula is for the tangential velocity of the shaft, which you need to remember here, and this will be used in other things as well. So mu, or your dynamic viscosity, right, is equals to pi into d into n by 60 meter per second. Now d is the, what is d? I'll just write here, d is the dia of shaft. Pi don't need to write. N is the rotation speed, right? Rotation speed in rpm, and d is die of shaft in meter, obviously, because we will deal with these things, right? So this is it, and this formula will be used, and again, for the power, another formula will be used for power lost, right? Okay, for power loss, the formula which will be used is, I'll write it later, it is P equals to power, I'll just write the formula once because you need to know it. So power lost, P is equals to 2 pi n t by 60 watt. This formula is also used in other numericals, not only just this numerical. So now here only thing you don't know is your T. Now T is torque here, right? And torque is equals to force into d by 2. F is force. Now this F force also is equals to your tau into A. So stress is Newton per meter square and area is meter square, so this will give in Newton. So these are the formulas which you need for the numericals, additional formulas. So let's just begin solving the numericals here. Okay, so I'll just start again because I've just just deviated from this. So mu is equals to 0.6 Newton second per meter square, so which is this the dynamic viscosity, and d diameter of the shaft 0.4 meter, which is given, n which is the number rotation speed in rpm 190 rpm, this is given, l is the this length of this bearing of sleeve length. So sleeve length is L is 90 mm, which is given, you could just write it 0.09 meter directly. And then this this another thing which you have is the thickness of the oil film. So thickness of the oil film, just take it as T is equals to 1.5 mm is given, so 0.0015 meter. So like this you can see. So let us find out the tangential velocity of the shaft. So okay, I've just done one thing error here. So this is not this mu, this is actually u, right? Tangential velocity of the shaft, this is u, there is no relation with the mu. Okay, so tangential velocity of the shaft here, we know, just find out the tangential velocity of the shaft. This will be u is equals to pi into d into n by 60 meter per second. So is pi, we know, directly put in calculator pi, no need to just break it in 3.14 into 190 divided by 60. So if you do this in calculator, let me do it right now. I'll just do pi into 0.4 into 190 divided by 60. So it will come as, it is coming as 3.979. So I'll just take two places, u is equal to 3.98 meter per second. So I found the tangential velocity. Now once I found the tangential velocity, I'll find du. Du will be same, right? Du is equals to u minus 0, and which in turn du means du is equal to same as u, 3.98 meter per second. So it will not change. And next thing is dy. Now dy, we already know that what is dy, it is actually T. Okay, thickness of the oil film, this is actually dy. So you can just write simply dy here instead of T, it will be less confusing. So dy is 0.0015 meter. So we know dy here, and now time for the relation, tau is equals to mu into du by dy. So this is the thing here, and is equals to 0.6, mu is 0.6, we know, just put the value 0.6, and to du just we have found out, du is 3.98 meter per second. So 3.6 Newton second per meter square into 3.98 meter per second divided by dy is 0.0015. So 0.0015, and just do this in calculator right now. 0.0015 and the unit is obviously meter. So just to do this, I'll do this in calculator right now. 0.6 into 3.98 divided by 0.0015. This is looking like 3. Okay, 0.0015, and the answer is 1592. So 1592, if you just look at the units, it will be 1592. It will be Newton per meter square. No meter cancel, and second will also be cancelled here. So it will remain, what is remaining, Newton per meter square, which is the unit of this tau. And now tau is also called the shearing stress. So shearing stress we found out, and the shearing stress unit is your Newton per meter square here. And now once we have the shearing stress, now we'll find out the force using the formulas which we had listed earlier. You just want to remember the formula. Force is equals to tau into it. This formula already we know, no need to remember this, because force is equals to this stress into area. If multiply area, then it will come as force. So if you just simply 1592 Newton per meter square into the area in meter square. So what is the area in the thing? So now what are the things which are given here? D is given, pi we already know, so the area will be actually the circumference. So one thing which we had I had missed here in the question is the this diagram. So this diagram will also be required here for the shaft. I'll just draw it here. The diagram can just draw it here small. So this is the shaft here. The question will be, diagram will be given here, because without the diagram you cannot solve the problem. I had thought that we can do it otherwise, because this is this the shape. This is the sleeve, right? This is the sleeve, and this is the shaft. Actually this is the shaft, and uh, this is the shaft dia, right? 0.4 meter which was given, and this is your oil film thickness, and oil film thickness is 1.5 mm. So this is it. So now as you can see, the shaft is your shape is cylindrical. I'll just draw it big here, because otherwise it might be confusing, right? So I'll just draw it big, little bit bigger here, bigger size. So this is the shaft. So this is the shaft, and this is the shaft dia. Now this is 90 mm. This is the sleeve. Now this is thickness of the shaft, 0.4 meter, and this is the thickness of the oil film, 1.5 mm. So this is the diagram, right? So now the area, which area it will be the circumference. So circumference of this cylinder, we know this 2 pi r or pi d. This is the circumference of a cylinder, right? So similarly this formula will be used here, pi into d. So it will be pi into d, that is 0.4. Now if you want to find out this this area, 2 pi r or pi d is the circumference of this, okay, pi d l. If you do pi d l, now if you they have this cylinder like this, and this is this d and this is this l, okay. Some in the mathematics we take this as h, right? So if you want to find out the surface area of this cylindrical part outside, so the formula was 2 pi r h or pi d h, right? This was the formula for the the surface area of the outer part, right? So this was the formula, 2 pi r h or pi d h. So that we'll do here, pi into 0.4 into h. H is here L, that is the length of the shaft, which is 90 mm or 0.09 meter. Now it will be given as, if you just do it right now, 1592 into pi, simply I'll put pi in the calculator, into 0.4 into 0.09, it will come as 180.05. So it will come as 180.05 Newton. So F we got from here 180.05 Newton. So once we got the F here, now we can easily find out the torque. Now torque, I had already told you the formula, or else you can already know, because mechanics that is a lot of mentioned in this. Torque is equal to force into distance. Now torque will act on the mid part, okay, so it will be distance by 2. So D is 0.4. Now torque will, if you just see here, 0.4, torque will act in the center, so it will be 0.4 by 2. So F into D by 2, this will be the torque in the shaft. So F we already know, we have just found out 180.05 Newton. D we know, that is 0.4 meter by 2. So just multiply this and it will come as 36.01 Newton meter. The torque will be this much. And then the last but not the least, the main thing which you need to find out is the power lost. So all the formulas I had already given in the start, you have to remember those formulas, and not only for this numerical, other numericals also. 2 pi n t by 60. Now we know what is 2, we know what is pi, we know n is the speed in the rpm, and it is 190, right? And torque we just found out, right, which is your 336.01 Newton meter, and then 60. So the whole thing will come in watt. If you just calculate it, power, just calculate in calculator. 2 into, I'll just do it right now, 2 into pi into 190 into 36.01 divided by 60, it will come as 716.48 so watt. So it's very important to remember this formula. So today we'll keep it till now, and going forward, you just make sure you remember the formulas which have been taught, and in the next lecture we'll just move on to surface tension. If just remember these two formulas, you'll be able to solve a lot of numericals, and also attempt some of the MCQs also. So that's all for today. Make sure you practice and get ready for the next lecture. Okay, bye bye.